Hello everyone and welcome to my new stream. How are you doing, guys? We are finally back on learning OpenGL. Finally, after 3 days. Damn, that's not good. 3 days. Oh my god. But we are back. We are back. Let's do a little bit. Let's recap of what we did so far with this stuff, right? So I'm following this series to learn OpenGL, and I'm doing online streaming because why not? And we definitely need to do a full recap of what we did. If and if I remember what we actually did, like if I remember everything correctly, right? So we have the glue.h, that is the library that we use to link with the with the with the functions that are installed already in our GPU. We are binding it to use it on our C++ API. So when we use the C++ OpenAI, wait, what the fuck? Why did I say OpenAI? When we use on C++ API, we are just pointing functions, right? And to call it from the GPU, and the GPU and this binding actually differs on each platform apparently, and that would be a mess. But luckily, we have Glue Edge that does the job for us. Then we have GLFW view, the library that provides a little help with handling some stuff like window and event systems, right? And then we have the assert macro, gl call, which is like we on OpenGL we could have errors. This errors are basically, I don't know, like they aren't that good. Like we use GL call to pull out all the errors that some OpenGL functions generated. We print the file and the line just to keep track of what we are doing. And it's called in loop because we have to pull everything out, right? Like we have to constantly ask OpenGL until we don't have any errors to display left, right? Kind of annoying, but that's basically how OpenGL works. Then we have the fragment shader, and then we have the other type of shader, um, the vertex shader and fragment shader, right? We have this too. And then we have to create the program. We have to compile the shaders from the source code, and then we have an ID. Everything in OpenGL has an ID. Like a shader has an ID, a program has an ID, and the buffer has an ID. Everything has an ID, right? So let's go here in order. So we have a window. We initialize glfw, and if it fails, we will exit the program. Then we will create a window, and if the window fails to initialize, we will exit. Then we will create a valid OpenGL context, so we can that's for setting the FPS. But we create a valid OpenGL context to initialize glue in it, and if it doesn't initialize correctly, we exit the program. Then we pull out as a string the version of OpenGL we are using. Then we have an array. We have an array of floats, right? This is okay. And this is pretty interesting because we have, this is an array, like this is an array of a couple of two floats, right? It's virtually an array of two floats, right? But we are using the indices to, map this, the positions of the vertices, right? We bind everything here. So we have the buffer here where we store this data, right? And then we create one buffer using this function, right? Then we bind it using GL array buffer. We pass the ID because this returns ID, right? Because we are passing as a pointer. We are passing this the address of this variable, right? And then we have this part right here, and then we allocate this. I still think this is an allocation function to the sides of 6. I'm honestly not sure. Is this supposed to be 6? Like, we're passing positions, but we have 8 elements, right? Actually, we only have 4 times 2, so this should be 4, right? And then we have sides of float, and then we pass the actual buffer, and then we pass the mode. And honestly, I'm not sure what's the difference. There is static, dynamic, and stream, and then there is read, draw, probably write. I don't remember exactly, but this is basically it. Then we have GL enable vertex attribute array, which enables the position attributes for the vertices, right? And then we have the pointer. Here we have to set, honestly, what that is. Like, this is the float. We have 2 floats, but okay, this is the sides of individual of each element, right? Of each attribute. We have 2 floats, x and y. We indicate with 2 floats, and we pass 2 times size of float, right? Then we have this, which is, I think this is the index, right? The index specifies the type. In this case, we are having the position attribute, right? Then we have 2. This is the dimensions, right? The dimensions, we are working on 2D, so we have to pass 2. Then we have GL float because we are using floats. Then we have to pass GL floats because float values are already normalized. And then we pass this 0 that I don't remember what that is actually. Can we get the... I don't remember what that is. Let's see. We can't see it right here. That's the pointer. That's the fucking pointer. Oh, that's the pointer of the, probably of that of this thing, and we pass it null. That's because it is binded, right? It is bound, probably. Then we have index buffer object, and this is a index buffer This is index buffer, which we reuse the vertex positions to create actual vertex. I mean, to create like mappings, right? So we create three triangles with this. So we are using the first one, then the 0th, then the first, then the second, then we have the second, the third, and the 0th. That's basically it. So then we have shader program source, which is a struct we defined that contains both of the vertex and the fragment shader, right? And then we create the shader. When we create the shader, we call this function, and on this function we create a new program. Then we compile both the vertex and the fragment shader. Then we attach them. We link them, and then we validate the program. And if everything is done correctly, this shouldn't be here. So yeah, GL get program IV. That's the program. In the program ID, then we set the flag. It's GL link status, and then this is where the result will be returned. Then we delete the shader to free memory or something, but we don't need them anymore because the shader, which is that are programs that are run on the GPU, are already compiled, linked, and ready to be executed. So we return the program ID. Here we compile the shader like this. So the same thing applies here. Oh god. Right here, right? So the thing is, we actually have. So we have GL get uniform location, right? So before doing all of this, we have to explicitly tell OpenGL, the API, that we are using this program, right? Then we have the int location, and that's probably GL get uniform location, right? So we have uColor, right? And uColor, we pass this, right? We have color, okay, and then we assign the location, right? Is it like that? Not sure, honestly, but we have, for some, why do we pass the buffer? Wait, why do we pass the buffer? That doesn't make any sense. I don't know, honestly, why do we have to pass the buffer? That's quite confusing. Like, what does oh wait, I know, because we have to assign it, right? Yeah, that's because we have to assign, actually. Then we assert the location is valid, and then we have GL uniform for F, and then we assign this, and then we draw and render everything. That took me 20 minutes to explain. Well, actually, there are 4 minutes are part of the intro. So, god fucking damn it, go here. So we can say that it took 14 minutes. So now let's keep following the series. Let's try to understand more about it. Let's try to do more about it, right? So This is the 7th hour of work for me, and we are probably gonna stream for 2 hours today, and then I'm gonna stream the we are gonna continue our form application development on another stream, right? So let's keep going. So what we have right now.
Hey, what's up guys? My name is Eterno and welcome back to my OpenGL series. So today we're going to be talking all about vertex arrays in OpenGL, of course. So far, we've been talking about what a vertex buffer is, what an index buffer is, or an element buffer. We've talked about shaders, we've talked about a lot of kind of basic concepts of OpenGL and even graphics programming in general. But OpenGL actually has something called a vertex array. And at first glance, you might be like, well, vertex array, vertex buffer, what is the difference? They sound extremely similar, and they are. And to make it even crazier, so to speak, I mean, this isn't particularly crazy, but to make it even crazier, this isn't really something that exists in other rendering APIs like DirectX. Vertex arrays are a bit of an OpenGL special, or an OpenGL original, if you like. And what they basically are a way to bind buffers, vertex buffers, with a certain kind of specification for the layout of that actual vertex buffer. So let's take a look at what I mean by that by just looking at some code real quick. So in our application, we have this buffer that we're creating over here, specifically this array buffer, which contains all of our vertex data. And actually, you may have noticed from previous episodes that I have 6 written here as a size, so as if we have 6 vertices. Clearly, we have 4 according to this. That's a bug. Let's fix that by setting this to 4.
Yo, that's what I noticed before. Holy fuck! Wow, this is. I feel so good. Sorry. I'm just learning, and for me it's a lot.
But this vertex buffer contains these vertex positions, all of this vertex data, which in this case is just vertex positions for 4 vertices. And
Also, why did I start from one? Yeah, that was confusing. I was a bit confused at the start, but I actually made a mistake here, so let's correct that.
then after we've created the buffer and we've bound it and we've set the data and all of that, we actually enable the vertex attrib array and then specify the layout of this actual data here by saying that basically every vertex, each vertex is 2 floats. And then that's the stride, kind of vertex to vertex, right? And we also specify like the offset of this attribute and all of that. So we basically just specify the layout of this actual vertex buffer. Now what a vertex array object actually lets us do is kind of bind that vertex specification that we specify by using this vertex attrib pointer to an actual buffer, to an actual vertex buffer, or a series of vertex buffers, depending on how we actually organize this. So instead of us having to actually explicitly specify the vertex layout every time before we draw, well, okay, so right now obviously we're not drawing anything complex, so it might be a little bit difficult for those of you who are new to OpenGL to actually get what I mean by this. But what we actually need to do currently to draw this, if we had multiple objects on the screen, multiple meshes, multiple vertex buffers, all of that, is we would basically have to bind our vertex buffer, bind our index buffer, and then draw our actual object. But after we bind the vertex buffer, we also need to actually specify that layout. Because if we later down the road bind another vertex buffer which has a different layout, then we have to actually have a way of saying that, well, this buffer has this layout and this buffer has the other layout. It's not actually stored in the buffer. You might think that because we actually, in our code, we bind a buffer and then we actually call this vertex attrib pointer, that this state is kind of tied to and saved with this actual buffer object, but it's not. This is something that is actually technically tied to a vertex array object, and thus we need to call it every time. In fact, let's take a look at what our code would look like if we were actually kind of binding everything that we needed to render every time. Because right now what we've done is we've bound all of the kind of objects that we have, because we only have one of each. We have one shader, we have one vertex buffer, one index buffer, and all of that. If we actually were to have multiple objects, we would have to rebind everything we need for the current draw every time. So let's take a look at what that will look like. What I'm going to do is when we actually set everything up over here, I'm actually going to unbind everything. So I'm going to call GL bind buffer. In fact, let me just copy everything from here. So we need bind buffer. We need this bind buffer, which is our index buffer or our element buffer, and then we have this use program. Okay, so what I'm going to do is basically call 0 for all of these, right? So GL use program 0 and bind buffer 0 for array buffer and index buffer. So what I've done here is I've basically unbound everything. So when it comes time to draw, what we need to do is actually bind everything that we need for this draw elements to work, so that
we have to constantly bind everything.
render everything correctly. And this will include, setting up any kind of state that we may need. In this example, it's very, very simple. So all we really need to do is just bind these things, right? So before we draw this, I'm going to bind this shader, right, by calling GL use program, and then we can set the uniform once that's bound. Then I'm going to bind my buffer, which is going to be just buffer, and then I'm going to bind my index buffer, which I believe we called IBO. Okay, cool. And what I actually need to do, which might not be apparent here, is I also need to get this GL vertex attrib pointer and run that again. Now, you will probably, if you end up disabling vertex attrib arrays, you'll probably have to do that again. So let's just copy this and this whole block here because we might need it. Like that. Okay, so this is what it kind of ends up looking like. We bind our shader, we set up our uniforms, we bind our vertex buffer, we set up the layout of that vertex buffer, and then finally we bind our index buffer, and then we call GL draw elements. Let's run this code and see what happens. And you can see we get the same result as before. Perfect. So the part that is interesting here is these two. Do we have to do these every time? And the answer is, well, yes, because they may have changed if we draw another object with a different layout. So vertex array objects are actually what contain this state. So if we utilize vertex array objects properly and were to, for example, make a different vertex array object for each piece of geometry that we actually draw, or for each draw call basically, then all we would need to do theoretically is just bind the vertex array object, and that's it, we're done. Because a vertex array object will contain a binding between a vertex buffer or buffers and that actual kind of vertex specification or that vertex layout. So in other words, so vertex array objects are actually what contain this state. So if we utilize vertex array objects properly and were to, for example, make a different vertex array object for each piece of geometry that we actually draw, or for each draw call basically, then all we would need to do theoretically is just bind the vertex array object, and that's it, we're done. Because a vertex array object will contain a binding between a vertex buffer or buffers and that actual kind of vertex specification or that vertex layout. So in other words, vertex attrib pointer actually will bind an actual vertex buffer, an array buffer, so something bound to this GL array buffer slot. It will bind that with that actual layout, with that specification. And that works whether or not you have a single buffer like we do here, or if you have multiple buffers. And we'll definitely end up talking about kind of a single buffer and multiple vertex buffers in the future as well. And so the way that we draw things changes from being bind our shader, bind our vertex buffer, set up the vertex layout, bind our index buffer, and then actually issue that draw call. It changes from that to just being bind our shader, because obviously that stays the same. Then we bind our vertex array, and then we bind our index buffer, and then finally we issue that draw call. So basically, binding that vertex buffer and setting up its layout just becomes binding that vertex array object, because that contains all the state that we actually need. One other thing that I need to mention here is that, technically speaking, vertex array objects are mandatory, and they are actually in use right now, which is why I said that even without us creating them, this state is still maintained by the vertex array object. The thing is, the OpenGL compatibility profile, which is what we're actually running here, it's like a mode for OpenGL to basically run in. The compatibility profile actually creates a vertex array object for us by default, and that's what 0 is. Whereas the core profile does not. So we actually need to explicitly create an OpenGL vertex array object by ourselves and bind it and make sure that's all up and running manually if we're using the core profile. So to demonstrate this, what I'm going to do, I'm just going to hit F5 to run my code just to see if everything's running correctly, and you can see it is. What I'm going to do now is actually tell GLFW that I want to create a context, this OpenGL context. I actually want to create this window in this context with the core profile. And the way I'm going to do this is basically just by pasting this code in here. So what I'm doing here is I'm setting a GLFW window hint which says that I want my major version to be OpenGL 3, minor version to be 3, so it's OpenGL 3.3. And then this is the important code here. I'm setting my OpenGL profile to be core. Now currently I've got compatibility on. So if I actually just set this to compat profile and hit F5, the only thing that you'll notice that changes is our actual version of OpenGL. Instead of using the absolute latest one that we have available in our drivers, it's using 3.3, which of course is the one that I specified. And you can see that of course my code still works perfectly. However, if I change this to be the core profile like this and hit F5, we're actually going to trigger an assert, as you can see, when we try and enable this vertex attrib array. And that is because if we go over here into the OpenGL documentation here, this Kronos site on vertex specification is actually really good, and you can see the line I've highlighted here. The compatibility OpenGL profile makes VAO object 0 a default object, whereas core does not, it's not an object at all, right? That's what's actually happening here.
Wait.
The compatibility OpenGL profile makes VAO object 0 a default object, whereas core does not, it's not an object at all.
So there are two profiles, right? We have the compatibility, and then we have the core profile, right?
That's what's actually happening here. As you can see specifically, if we look at our actual console here, we have an OpenGL error 1282, which is GL invalid operation, on this line of code, enable vertex attrib array. So let's again open the documentation and look at GL vertex attrib array and see what 1282 actually means. And you can see over here that one of the causes of this invalid operation is if no vertex array object is bound. So that's what's happening. We don't have a vertex array object bound, therefore we cannot specify a vertex attrib kind of specification or enable a vertex attrib array. So what we need to do now to fix this in the core profile is actually create that VAO, that vertex array object. So let's do that. It's really easy to do this. All I'm going to create that VAO, that vertex array object. So let's do that. It's really easy to do this. All I'm going to do is before we actually generate this buffer and create it, I'm going to type in unsigned int VAO, which will hold that actual vertex.
Okay, so let's do that. So we create the vertex array object, right? So we have unsigned int VAO. Then we have probably a GL call, right? Then GL generate buffers, probably something like this.
Vertex array object ID. I'm then going to GL call a GL gen vertex arrays. I'm going to
okay. It's actually different. Gen vert GL gen vertex arrays. Wait, what the? Wait, what did it just? Wait. Hold on, let me just. I saw something that. Wait, Apple SGIX EXT. What the hell? So let's do that.
One of them and then store that ID in that VAO variable. So it's the same as with buffers, of course, except we're generating vertex arrays. And then finally, I'm going to bind it. And GL bind vertex arrays, there's no actual target, so we just specify the ID of what we want to bind like this. So we don't have a target like GL array buffer or anything, it's just bind vertex array and then the ID. So I've still got the core profile on, which is what asserted before with an OpenGL error. Let's try and run this now and see what happens. And you can see I don't get any errors and I still get the same result. Okay, so that is us explicitly creating a VAO, and that's
so wait, hold on, let me just
that we have noticed the changes that of course our actual
wait, what do we let me just copy this part. So what we are doing here is we are using glfwu window hint glf wvu glf. Oh my god, glf view context version measure. Now we have 3, and then we have minor, and then we have the profile, right? Here we specify the profile. So we have OpenGL profile, and then we specify glfwview OpenGL core profile. OpenGL core profile, like this, right? Okay. So we created a vertex array object, right?
Profile to be core. Now currently I've got compatibility on. And then finally I'm going to bind it. And GL bind vertex arrays, there's no actual target, so we just specify the ID of what we want to bind like this. So we don't have a target like GL array buffer or anything, it's just bind vertex array and then the ID. So I've still got the core profile on, which is what asserted before with an OpenGL error. Let's try and run this now and see what happens. And you can see I don't get any errors and I still get the same result, okay? So that is us explicitly creating a VAO, and that's specifically how you use VAOs as well. We just generate one, we bind it, and then we have the ability to actually bind a buffer and specify a layout for it. Now, what's really interesting is that if we scroll down here, we no longer have to actually do this enable vertex attrib array or pointer code, okay? And we also don't need to actually bind the buffer. Let's add to this GL, well, to us clearing all of our GL states, GL bind vertex array, so we'll be binding vertex array 0, just so that we're clearing everything. And then over here, I'm just going to bind vertex array VAO. So you can see that I'm not binding my vertex buffer at all, and the currently bound buffer to GL array buffer is actually 0, right? I'm just binding my vertex array and just binding my index buffer, and that's it, okay? Obviously I'm binding my shader as well, and then issuing that draw call. Let's hit F5. Check that out, I still get my rectangle rendering correctly. So what's actually happening is we're linking that vertex buffer to this vertex array object, and the question is, what code is actually doing that? And it might be a little bit confusing if you don't know how it works, but of course I'm going to tell you how it works. When we bind a vertex array and we bind a buffer, nothing actually links the two. But when we actually specify this vertex attrib pointer, we're saying index 0 of this vertex array is going to actually be bound to the currently bound GL array buffer. Okay, so this, in other words, is a line of code that actually links this buffer with this VAO. Okay, if I was then to bind a different buffer and then call GL vertex attrib pointer with the index 1 after enabling it, of course using this line, then I would actually be saying that inside this array buffer, index 1 is actually pointing to a different vertex buffer. And again, we'll definitely talk about multiple vertex buffers in the future, as well as having one buffer with everything in one buffer, because that's also an option. So that's how it actually works. And because we've actually specified this vertex attrib pointer, and we have a vertex array bound, and we have an actual buffer bound, the two are basically linked, which means that all we have to do is just bind our vertex array. And then index buffers, of course, are a separate thing completely, which is why we still need to bind it, and then we can draw elements. So you can see this code has become quite a bit cleaner, and that's all we have to actually do. So the big question is, what do I do? Am I supposed to use vertex array objects like all the time? Can I just be setting a vertex buffer and a vertex specification? What's optimal? Like, how do I do things? All of these questions. What happens when we have multiple meshes that we want to draw? I know that a lot of this is incredibly kind of simple because we're just drawing one object and it happens to be really, really simple. I am going to start abstracting all of this code out into classes, and as soon as I do that, I think I want to actually start doing that next episode. As soon as that's done, it's going to be really easy for us to actually create a bunch of different vertex buffers, fill them with data, and draw multiple objects on the screen. And we'll probably have to set up some other things like maths and all of that to make that happen. But the idea is, what is the deal? Like, should I be using multiple vertex array objects? Can I get away without using them? What's the deal? Now, what I'm about to tell you is going to be a little bit opinionated and probably a bit vague, but the thing is, there's no better way for me to actually explain it to you, because the answer is it depends. So first of all, let's take a look at what's happening here. If we use the core profile, which I'm currently using, we have to create a vertex array object. If we just use the compatibility profile, it doesn't mean there are no vertex array objects. It just means that we have one default. We have a default one that's bound and set up for us to use. If we're in core, we have to create one ourselves. Now, what you could do, technically, is you could just create one vertex array object like we did here, and just leave it bound for the duration of your entire program. So you always have one vertex array object bound. And then what you can do is bind a vertex buffer and specify a vertex layout every time before you actually end up drawing your geometry. So in other words, you're kind of doing the same thing that we did before we introduced this vertex array object. So as if we were using that compatibility profile. That is an option. And that's kind of a way for you to say, I'm ignoring vertex array objects entirely. I'm just binding one kind of default one by myself because I need to, otherwise my program won't run. Otherwise I won't be able to render anything, because OpenGL actually mandates that in the core profile. So that is one option. You could just ignore vertex array objects by binding one, forgetting about it, leaving it bound, and then every time you actually have to draw something, you bind a vertex buffer, you bind something into the GL array buffer slot. Then you specify that you enable any vertex attrib arrays you have to, and specify that vertex attrib pointer stuff so that you map your layout. And then you bind your index buffer, and then you render, right? And obviously you have a shader bound and any other state that you might have to set up, right? You could do that. That's one option. That's option A. Option B is, for every piece of geometry that you create, you basically create a vertex array object. Then you specify that specification once, so you enable any shader bound and any other state that you might have to set up, right? You could do that. That's one option. That's option A. Option B is, for every piece of geometry that you create, you basically create a vertex array object. Then you specify that specification once, so you enable any vertex attrib arrays you need to. You specify GL vertex attrib pointer as many times as you need to set all of that stuff up. And then you obviously bind a vertex buffer as well before you do all that. And then, when it comes time to draw, you just bind a different vertex array object basically every time before you draw your geometry. And then you bind an index buffer, and then you call GL draw elements or whatever draw function you're using, okay? So you either have one global VAO for the entire program, and then you bind different buffers and different vertex specifications every time, or you have a separate VAO for each piece of geometry or each unique piece of geometry or whatever, right? Which one's better? Again, it's hard to answer. So an easier question to answer is, which one is more optimal? Which one should I use? Which one is faster? Is it faster to just bind a buffer and specify that specification?
I don't. The hell?
Every time, that layout, or is it faster to bind a different VAO every time? Now, in the past, it has been faster to actually just have one VAO and then bind everything every time. I know that for a fact, and NVIDIA actually has a paper on that. I'll link something in the description. It's like, I think slide 67 or something of that. I'm really just talking from memory here, of a source engine, Valve source engine kind of presentation, where they actually, NVIDIA specifically discouraged the use of VAOs and said just don't use them. That was a while ago. I haven't done any recent benchmarks on this, so what I would recommend for you to do is use VAOs, right? Just use them. OpenGL recommends that you use them, so use them. Now, just because a specification recommends that you do something does not mean that it is the best thing to do, okay? This is the real world. Things work a little bit differently than the ideal case where VAOs just work, right? And they're faster. So what I recommend you do is that if you really, really care about performance, and you absolutely need to squeeze every last bit of performance out of all this, you actually run some tests. So in your environment, on your platform, on your device, whatever it is that you're actually doing, try in your actual production environment, try to actually use one global VAO versus a VAO for each object, and get some real numbers out of that, and see what works better for you, because it is going to be circumstantial. It is going to be different depending on your environment. So benchmark that, profile that in your environment, and see whatever option works better for you, and then stick with the one that works better for you, okay? It's really difficult for me to answer questions like this because It depends, right? Again, I haven't done any recent benchmarks on this. In the past, I have found using one global VAO to be faster, but that was years ago, so I cannot talk about this right now with current drivers. So what I might do in the future is actually benchmark this kind of engine or whatever that we have right now, this little sandbox application, um, is nowhere near mature enough. It doesn't have enough stuff going on for me to actually test it. Otherwise, I would probably throw a little benchmark. Actually, yeah, drop a comment below if you want me to benchmark this, and I'll see what I can do. If you yourself run a stress test and benchmark this and do all that, you can leave your results in the comments below. I'd love to read them. But the idea is, again, it kind of depends whether or not you want to use VAOs. I will, from now on, be using VAOs just because I don't particularly care about performance right now, and it is what OpenGL recommends that you actually do. However, do check out that paper or presentation or whatever that I linked in the comment section, in the description box below, if you're interested in that, and definitely test it in your environment for your use case, on your platform, on your device, whatever, to actually see what you get, because that's what actually matters. Anyway, I hope you guys enjoyed this video. If you did, you can hit the like button. If you want to support everything that I do here on this channel, then head on over to patreon.com/thecherno. You'll get some cool rewards such as getting videos early, access to all of the source code repositories for every series that I make on this channel, including all the code that I've written here today, as well as like a diff between each episode so that you can easily see what I've added and all that. There are some other pretty cool rewards, like for example, all of the partners, which is the highest Patreon tier. All of us, we hang out like once a month and just have like an hour-long conversation about life and about programming and about development and all that. So that's a really great time. So definitely check out those rewards there. The biggest thing you're doing is obviously helping me to continue making these videos, which is pretty cool. And as always, a huge shout out to everyone who supports what I do, because without you, none of this would be possible. Next time, I think we're either going to talk about maths, or we're going to probably start abstracting all of this code out. Let me know what you want to think. Let me know what you want to see in the comment section below, and we'll see what we actually end up doing. One thing I wanted to mention was, if we talk about maths, we'll have to use a math library, as well as probably talk about how things like projection matrices work and matrices in general and all of that. So that might be a long thing.
Yo.
It's something we have to do. So the only thing I can say about maths is you got to learn to love it, because as a graphics programmer, you're going to be dealing with maths quite a lot, because that's how pretty much everything works. Anyway, I hope you guys enjoyed this video. I will see you guys next time. Goodbye.
Yo, that's fucking cool. I'm fucking studying matrices right now, and it's, oh my gosh, it's literally right here. It's right here. This is mathematics for machine learning, and this is fucking cool. I'm studying it right now. Holy fuck, this is, oh, I like how things link together. But yeah, I'm also, I don't have it right here, but I'm also developing a C library for it. So we can also just, hold on. If we go here, so if we go here, right? So we are live, luckily. Let's go here. That's the library, right? Let me check if the header file is visible, so we can, that's the header file. Yep. Let's see if I scroll this. So we have this part, right? So let's see if everything works. That's the header file, and I didn't show it right here, but it's definitely somewhere. But yeah, we are developing the actual API. I mean, the actual library for just to learn stuff. I will publish everything probably on a website, and this is the website I have. I got disconnected. Yeah, I'm back. Okay, I got disconnected. That's okay. So right now, let me just check what is running. Okay. But that's cool. We are using matrices. That's what I want to learn. That's what I want to learn. Right? Very nice. Now let's probably, yeah, we'll probably see it on a few episodes, right? This is the 12th episode. This is the 19th. Yeah, we still have 7 episodes. Actually, we ended watching this, so this is the 13th to 19. We have 5 other episodes, but that's good.
Hey, what is up guys? My name is Ichano and welcome back to my OpenGL series. So today we're going to have a nice chill episode in which we just talk about how we're going to abstract some of the code that we've actually written in the past episodes out into some classes so that we can use it more easily as we start to get into more complicated OpenGL stuff, which is obviously where this series is headed. So I did mention a few times throughout creating this series that I really don't want to make this a game engine series. I don't want to make it like hey, we're going to build some kind of OpenGL engine or like a rendering engine or anything like that. I don't really want to spend too much time moving code around and setting stuff up and making it absolutely bulletproof and absolutely perfect, because that's not the point of this series. This series is just me showing you how to use OpenGL. However, in the real world, in order to actually use OpenGL, you do need to perform some kind of abstraction of some sort, because otherwise you're just going to end up having a pile, just a messy pile of code that doesn't make much sense to you. It's going to be extremely verbose, and you're just going to, it's going to be difficult to debug. There's all sorts of issues, and it's going to be extremely difficult for me to show you, for example, how to implement shadow mapping if I'm all doing it in one file with just raw OpenGL kind of code, because it's not going to make much sense. So what I'm going to do over the next few episodes is start moving code out into classes and showing you how we can kind of, I guess, move common code around so that we can reuse it a lot of times, maybe parameterize it as well, and all that stuff. It's also a really good opportunity to show me a little bit, or for me to show you guys a little bit about how OpenGL can be abstracted and how it typically would be abstracted in a game engine, even though we're not going to go as deep into this as if I was actually writing a game engine potentially with multiple rendering APIs. It's going to be fairly brief and high level here, but still it's a really good chance for me to just show you guys how you would typically go about abstracting OpenGL anyway. So for that, and then there's the whole shader situation. That's probably it. If you really think about what we've done so far, we haven't done textures yet or anything like that, or